In this lecture, we're going to look at some general advice that can be offered in terms of how do we help improve the performance for programs, and particularly what we're thinking about managed languages here. So that includes Java, includes C#, and other related ones. But it will be a collection of general hints and tips that offer a bit of guidance that if we follow this, generally speaking, will give us reasonably efficient programs, or some things which help improve the efficiency of it. Within the course, certainly when we get closer to the second half of it, we'll have a look at C++ in terms of it as a language, how it works, and that will enable us to get under the surface and to explore the notions of performance and efficiency in a slightly deeper manner. For this particular talk, it really is quite a high-level overview and more guidance or pointers that we can use within Java. So we're going to start off first of all really just by introducing the notion of performance and explaining why it's important. And when we think about performance, it ties into the broad notion of optimization, that we're trying to optimize something to get it to be as best as it possibly can be. There is actually multiple things that we could try to optimize, and to a degree some of these are mutually exclusive, but it could be the amount of CPU time that is required to implement a particular task. It could be the amount of memory, either in memory or in terms of some storage that we use if we want to minimize that amount of memory. It could be in terms of network traffic and the amount of data that we have to send across a network connection, and again wanting to minimize that. So the process of optimization, of getting high performance, often comes down to trying to improve something or some aspect or some area so it's as good as the thing possibly can be. There's two means that we as programmers could try to accomplish this. The first one is through design. That whenever we are designing our classes and the structures and how they come together, we think about performance at that point, and we try to select designs and structures that are likely to be efficient in terms of how we implement them. The second way we can do it is actually through the implementation itself. So in terms of the structures that we use, how we code it, things like that, we can try to write our code in a way that means it will get to be executed fast. In this section, we're really just concerned with the latter notion of code optimization as opposed to design optimization. Now, that said, don't get the wrong impression about this. So generally speaking, for design optimization, it is always a good thing. We should always, when we are designing something, bear in mind issues of performance and efficiency, and that is the right point to think about it and to get things put in. If it's easier to do to that point, and it's likely to be that the returns are going to be more significant. For code optimization itself, you'd actually see the advice here is don't do it, or don't do it until you actually need to do it. So optimizing a piece of code, it will take time, it'll take effort, and often there is a cost associated with it other than the time and the effort, that it can make the code base less easily maintained, or at least less easily understood, or the risk of introducing bugs into it. So we always want to design things to be efficient, and in terms of writing things to be highly efficient, we only want to do that whenever we have a real need for doing so. So for Tony Hoare, he actually, a quote is attributed to him that we should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil. Slightly over dramatic interpretation of it, but in this sense we really want to optimize and to incur the cost of optimization when there's a need to do so. Process of optimization is quite straightforward. That we have, and assuming here that we're talking about the performance, the executional performance, as opposed to want to optimize memory footprint or something like that. But if it's a game, more often we're interested in making sure we have a good, stable number of updates and draws per second. So we'll set some target value, and if our game falls under that target value, then that gives us an indication we should do something to try to improve it. So the first one is we don't do this blindly. That's the wrong way to do it. There's a lot of good profilers you can get that will actually look at and monitor the execution of a program and tell you the areas where you're spending most of your time. So we run a profiler first of all. Having use the profiler to identify the areas where actually we're spending most of our time. We look at those areas and we come up with ideas or proposals about how we can improve it, how we can get those areas working faster. That may mean changing the design slightly. It may mean implementing it in a different, more efficient way. Finally, we introduce the changes to the code base, and we reprofile, and we carry on repeating this, looking at the performance until we get it down to our target level again. Worst case, if we're unable to get down to the target level, then we've got a fundamental issue that what we're trying to do, either we can't or we're not capable of programming it in a way that it can run within the constraints that we have. And that's a matter then of looking at that functionality and dropping bits or changing something more fundamental within it. We do have something that will help us in this. So as a managed language, so Java will have a virtual machine behind the scenes that is there, for example, looking after and managing our objects. Alongside that, Java, a lot of implementation uses a just-in-time compiler that they will compile the code just as it's encountered the first time. And we'll look at compilers later on in the course, but we'll see that one of the things a compiler tries to do is to make sure that it will compile our code so that it runs as efficiently as the thing can. So a compiler will actually try to optimize our code for us. And if you've got a good just-in-time compiler, you can see a list of some of the things it'll try to do here in terms of constant folding or copy propagation, inlining certain methods, taking out invariants that are within a loop, extracting them out of the loop, or if we have a small loop, unrolling it. And we'll look at all of those in a bit more detail later on in the course. But it is to say that the just-in-time compiler, depending on the device, depending on the platform, there's certain optimizations we can reasonably rely on the compiler to introduce. Saves us as programmers from having to do it. There is a cost of optimization that if you introduce optimizations, generally speaking, you can see here on the screen that the risk factors or how it will negatively impact upon your project. The first one is breaking code that actually works. So we'll have stuff that's been well tested and we can rely upon it. If it's running too slowly and we make changes to it, we may introduce bugs into this, either easily spotted or ones that will miss. It won't be easily spotted. Often, a lot of the types of implementation that we'll introduce, they will limit the reusability or the extensibility of the code. They'll make it less elegant, and that will then have an impact on the ease with which we can extend or build upon the code base. And generally speaking, introducing optimizations makes the code more difficult to understand, and that's an issue if you have multiple people using it or updating it. We want ideally everybody to be able to easily understand it. The bit at the bottom is quite important. That what we talked about here is trying to indicate the dangers of leaping into optimization too quickly and the cost that it can do. Now, that is not to say optimization is unimportant or you needn't at all worry about it, and it is certainly not an excuse to write shoddy, poor performing code. So the code that we write by default should be of decent performance, and if it's not profiling and not running as the way we want, then we go out of our way to put in fancy performance enhancement. And so if you like, these are really the additional thing, but it is no excuse to get away with writing shoddy quality code. We should never ever do that, even when we're implementing it just normally. The big reason why performance always matters on mobile devices. It doesn't matter if for a game we do want it to run as fast as we possibly can, but if you were writing some other activity that didn't have to run as fast, you would still want it to be efficient. Because if it runs efficiently, it means it does its job quicker, it uses less CPU cycles. This means we put less demand upon the CPU and we put less demand upon battery. And that means that overall then the battery will last longer and the user's going to have a better, more experience or better improved experience with their device. So efficiency, certainly when we're operating in an environment of mobile devices that are apart from some form of battery, we need to make sure all of our code, no matter what it is efficient. It's going to work well on those platforms. So let's have some suggestions then on the types of things we could do that could help us improve the performance. And these are rules of thumb at this point of the course. So we'll start off looking at the notion of creating objects. And the key takeaway from this is that anytime you use the new keyword to create an object, behind the scenes, there's a lot that happens. There's a reasonably heavy cost that's actually incurred in creating that object. So it's important. I mean, very easy for us to say, oh, knew this or knew that, but let's not underestimate what needs to happen to create and to produce us a new object. You can see some of the steps here. So we need to allocate some memory. And this, and again, if it's inheritance hierarchy, we have to get memory for the superclasses as well. That involves finding a region of memory that we can label as being used by that particular object. And depending on how memory is structured, how many objects we currently have, that may be easy, that may be difficult. We want to initialize it to some starting value. So generally we zero that memory, we clear it. And we'll probably have some type of constructor that will do startup sequences, and we'll call the constructor the superclasses constructor if we have one for building that particular object. So these are all things which need to happen anytime you create an object. And we need to appreciate that that's not cheap. There's a reasonable amount of computation involved in doing this. So good idea, where possible, to avoid creating objects if we don't really need to create them. Some hints and tips on how we can do that. So within Java, you have, for example, you can see here an int and also an integer class. So the int's a primitive, it's not a class, whereas the integer is a class that contains an int primitive. So wherever possible, we should favor the use of primitive values in our code, because it means that we're not creating objects to go along with it. Another way to avoid unnecessarily creating objects is to use what's known as lazy object creation, that you only create an object when you know you actually need to use that object. So the example we see here of the two 3-line ones, so the top one, string message is equal to something plus name. In this case, in line 1, we always create that particular object, always create it. But line 2 is conditional. So it's only if we want to print a message do we actually bother making use of that string message. So the form we have at the bottom, those 3 lines there, is better. If we need to print a message, then at that point, let's create an object that we're going to be printing out and carry on. So it lies it in, we don't unnecessarily create it. Another option is the use of string literals. So you can see this example at the bottom, where we've got 2 strings, well, they're both called string 1, but in one case we're assigning it equal to the literal, and inside inverted commas, hello. And in the second case, we are assigning it to a new string containing the sequence hello. So the character information is the same between them, but the advantage of using string literals is that languages like Java and C#, they will maintain a table of literals that have been defined. So strings are immutable. They can't change. Anytime you try to change a string, you get a new string as the output. So it means that if before in the code we have used the literal hello, it already exists, and when we encounter it later on, we're just going to give you a reference, a pointer to the existing version. So literals, if you need to reuse them, it's going to be much, much faster just simply to access the literal value. The bottom bit where we do have new, that's problematic because we'll always create a new string object. The other side of creation, and again this is a cost, is the deletion of an object. So Java, C#, they're managed languages. We can create a new object, we can use it, and then we're given the freedom and flexibility to simply ignore it. So we can create it in some method, we can leave that method. That object still hangs about. And in managed languages, there's a background process that runs, garbage collector. And every so often, it will scan through memory and trying to find objects or clumps of data that the programmer, the running programs, are not using anymore. And if it detects any of this sort of orphaned memory, then it's going to free the thing up so it can actually reuse it if any new objects need to be created. So it's a form of automatic memory management. It saves us as programmers of an awful lot of hassle. And when we look at C++, where we don't have garbage collection built in, we can see just how much effort is involved in doing this. But it does mean, again, that we have a process running in the background, And if we create a lot of objects and then get rid of them, it's going to be up to the garbage collector to do all the work in terms of getting rid of them, and that'll be a significant cost. So for a game in particular, it can be problematic, and the two main questions are: how often does a garbage collection happen? Is it twice a second? Is it once every 5 seconds? And when it happens, how long does it take to free up all of the objects that we've allocated and then discard it? If it happens reasonably infrequently, and there's been a whole bunch of objects created that then need to be deleted, this will take a long-ish period of time, and it's going to be enough to introduce maybe a frame skip into your game, that every regular it'll skip a frame, and that's going to actually be quite noticeable to the player. Alternatively, you can force the garbage collector to run if you want to, or set up how it runs, but if you were to run it very, very frequently, so in that sense you don't have any big delays coming in, but you'll be wasting time and effort running it when it doesn't really need to run. So there's a happy middle ground in all of this. General advice when it comes down to objects, and this is sage advice, is that wherever possible, we don't want to create new objects. We shouldn't do that. We should ask, can we, and if we can, we should be reusing existing objects that we've created. So we could use an object pool to do that. So it's a collection of objects. You can take them out from the pool to use them. When you're finished with them, you put them back inside the pool so they can be picked up and reused. And again, that's the whole notion of recycling and reusing objects. That saves us from creating and then having to delete an old object. And as mentioned, the notion of lazy instantiation, that we only create objects when we know that we really must create one, not before. That's all we're going to say then about object creation and deletion. When we get into C++, we'll look at it in a lot more detail. For calling methods is the next area. So if we have a look at, there's two examples over here for get accumulated length of some string. That says, okay, let's go through from the start of the string, id 0, up until the length of the string, and we're adding on, for example, 1 plus 2 plus 3 plus 4 plus 5 plus 6. That would be the sequence we would add up, where how long we continue in that sequence is based upon the actual string content that we're passing in. The two versions, they differ a little bit, and in line 3 in the top one, we have something that is potentially problematic. Now, it will actually, I'll say why it's problematic, but I'll say a little bit about why it may not be, depending on the just-in-time compiler. The potential problem with line 3, it's part of the for loop. So we will be starting I is equal to 0. We're going to evaluate some condition, and then we'll have some iteration condition at the end of it. So there's a risk that every single time we go around that for loop, we're going to be going to the string object and asking for its length. So we will be calling a lot of methods. And again, when we go into C++, we'll have a look at what happens when you call a method. It's quite an expensive operation. So in this case, we're calling the length method multiple times. That'll take a good bulk of time. The example at the bottom, which is slightly longer and is not as easy to read, has been optimized. Because we know that the string object, its length is invariant, or we can assume it's invariant, we can calculate it once at the start of the loop, and then just to use that calculated value for all of the iterations within the loop. And it'll run a good bit faster. Again, there's a little aside at the bottom that in terms of this, actually doing it through a design approach of actually calculating 1 plus 2 plus 3, you can do it mathematically. That's going to be ultimately the fastest way of doing this. But what you can see there is useful. Now, the reason why I say it may not be a cost, it does come down to the quality of the compiler. So strings are, as mentioned, they're immutable. They can't change. So if you have a getter method on a string for getting, for example, its length, it can never change for that string. So if the compiler is smart enough to understand the length of the string is invariant, it's not going to change, you actually could have the compiler saying, right, I know that's going to change, I'm going to calculate it up front, and then I'm going to reuse it within the loop. And the compiler could do that on our behalf. Another example here of where we are going to, for example, an enemy's array, we're getting out an element at a certain position and we're calling some method on it, and we're doing that again as part of another if. Okay, sort of shows you what's happened. The bottom example, lines 4 to 6, is a better one where we get the enemy once and then we simply make use and call the enemy for its different properties, as opposed to reaching into the array, abstracting something out and then checking that particular one. Chunky versus chatty calls is another way of looking at this. A chunky call is a call that you call that does quite a lot of work. A chatty call is something you call only does a little bit of work. And because there's a reasonable cost associated with performing or calling a method, you ideally want to be doing a good meaty amount of work any time that you call a method. Boxing and unboxing, probably go this reasonably quickly, but it's something to be aware of. What is it referring to? Well, it refers to creating a wrapper object that wraps up some primitive piece of data. So if you had an int, for example, Java has an integer class, and the integer class is basically something that boxes an ordinary int. Now, we've got a problem here because boxing and unboxing, you can see two examples, it happens automatically within the language. So Java will, if you give it a particular expression, it will try to box things automatically. And we ideally don't want this to happen. On the boxing side, you see the image down at the bottom. We've got two sort of lines of code. The first one with the number 123. It's a piece of primitive data. It probably declared somewhere within a method. It'll live in the stack, and 4 bytes of memory will be set aside to hold the value 123. Nice and compact. The second bit in line 2 says that we're creating an object for holding that integer. And there we will have the object reference, probably somewhere in the stack. It'll refer to some location on the heap where we've created that object, and then as part of that created object we'll have the primitive value 123. So it's kind of overkill in terms of how it sits out in memory. And did it with unboxing of taking the value out. Well, we've got to go to our temporary object, take it out, and then delete that temporary object. So the whole process of boxing and unboxing is expensive, and it's done automatically, so we want to make sure we're not writing any code that will trigger that type of process. They are computationally expensive. As opposed to accessing a piece of memory directly, you have to create objects, go through those objects, delete those objects when you're finished, and that's going to be a big waste of time. Again, just as mentioned. So data structures then. So I have one slide here that's going to try to get across some advice on how you can use, when you should use different types of data structures. And I'm aware that for people in this module, next semester, you'll be doing a full module on data structures and algorithmic analysis, and it'll get down to a lot more proper details. These are just guidelines. So if you have some data and it fits within an array, and the size of that array can be fixed for whatever task you're doing, use an array. It's going to be the quickest, most appropriate structure for that. If you know that you actually will have data that needs to grow or to change or is not of a predictable size, then an array list is going to offer you a good structure. If you need to either access values precisely to jump in at different locations in it, or if you're frequently jumping about the thing, there an array list is going to be good. A linked list, you can sort of view then as a sort of form of dynamic array list. It can grow, it can change. This is a good one if you need to sort of normally parse from one end to the next, and you're likely to be inserting or deleting or adding values into it. So a linked list is going to be a good data structure in that case. For a hash map, for a tree map, these are really for holding object pairings, where you have some value and you have a key associated with that value. You use your key to get the value out or to update it. You'd use a hash map if you just want to access randomly values and get them out by name. Hash map's going to be fine. If you have a need to iterate over the contents of that map, either from sort of smallest to bigger, then a tree map is going to be a good solution for that, because it will maintain it in a tree-like structure and you can navigate up or down that particular tree-like structure. But some rules of thumbs in the use of data structures. Key takeaways, we've only got a couple of them here. We've gone over a few simple guidelines in terms of things like object creation, avoid it where possible. In terms of boxing and unboxing, definitely avoid it no matter what you do. In terms of how do we access data, chunky calls, only making objects when we need to, not sort of recalculating things more times than we have to. All of those types of things, that they're guidelines, but if we follow them, there's a reasonable chance we'll write reasonably efficient code. That's what we should always be doing. It should be our baseline, is to write good quality code. If we get into optimization proper, this assumes that we have decent quality code, but it's still not sufficiently fast. And then we are going out of our way to either change the design or to change radically the structure, how we code it, to put in specific performance enhancement aspects. And that's really only what we want to do when we have a real extreme need of doing so. So this lecture, key thing to take away is just some of the general advice. Adhere and try to follow that as part of your everyday programming.